The graph of f double prime, the second derivative of the function f, is shown in the figure above. On what intervals is the graph of f concave up? So let's first look at a function that's concave up and see what its second derivative would do. So our graph would look something like this. Concave down is just this upside down. And now let's pick a few random points on the graph and look at their slope, since the slope is really the first derivative of a function. So if we look at tangent lines here, you can see what the slope would be at each of these points. And the second derivative is the rate of change of the first derivative. And since the first derivative is the slope, then the second derivative would just be the rate of change of the slope. So we need to look at how our slope is changing on this interval. Notice here it's a negative slope, then it becomes less negative, then it passes through 0 and becomes slightly positive, then it becomes even more positive and even more positive. So it's going from a negative slope to a positive slope on this concave up graph here, which means that the rate of change of the slope is positive, since the slope is getting bigger. So on an interval where the graph is concave up, the second derivative is bigger than 0. So now let's look at our graph. We have the second derivative graphed here. And we know that an interval where the function f is concave up would have to have a second derivative that's positive. So it looks like at -1, the second derivative is 0, and at 3, it's 0 as well. But between -1 and 3, the second derivative is positive, since its y values are positive numbers. So we can say the interval, which our function is concave up, is from -1 all the way to 3, and we're not including the endpoints, because at those endpoints, the second derivative is 0, and that would be an inflection point. That's essentially the point where it switches from concave down to concave up, or vice versa. So this interval here is the interval where the graph of f is concave up.